Good day. This is Dr. Mandis here. Just want to talk to you a little bit about bond types. The only reason I want to talk about bond types in my 112 class or my AP classes right now is just because you need to understand bond types to understand intermolecular force of attraction. So this is just to serve as a bit of a review of bond types. Now, bonding is just an attachment of particles together in a substance. Okay, it's nothing more fancy than that. It's like the glue that holds the particles together. There are going to be three main types of bonds that we need to talk about: ionic, metallic, and covalent. If we get to covalent, there's going to be three types of covalent. But to start, one of the easiest ones is ionic. Ionic bonds get a couple different definitions floating around out there. The easiest way to define an ionic bond is it's just an attraction of ions. Already, you got yourself a positive ion, and you got yourself a negative ion. Since they are opposite charges, they will attract each other. And what holds them together is purely that, just the attraction. What you end up having is that you have a positive ion. That positive ion is going to be surrounded by negative ions. Each negative is going to be surrounded by positives. Those aren't the best positives, but you get the idea. And every positive is surrounded by negatives. And I don't want to draw too many of them in because, good golly, there are a lot of negatives out there. Okay, and it keeps on going ad infinitum and keeps rolling. Which one is the ionic bond? Like if you're talking about this particular positive right there, which negative is it attracted to? All of them. And remember, this is just 2 dimensions. In 3 dimensions, it would have them on the other sides. The way those negatives and positives get arranged leads into its crystal structure. And we're not going to get into that, but I'm just letting you know it gets into that. As far as it goes, there's just an attraction of positive with negative. And it stands to reason from Coulomb's law, the closer they are together, the stronger that attraction. A stronger charge will attract more strongly. For instance, if you had a 2 positive, okay, with a 1 negative, that's going to be this attraction here is going to be a stronger attraction than, say, a 1 positive with a 1 negative. So it's exactly what you think it is, all right? More is stronger. The way that you can typically identify an ionic bond is you have a metal with a nonmetal, a metal with a nonmetal. Typically, metals form cations, nonmetals form anions, and so you get that cation with anion attracting each other. Sometimes it is difficult to see that something is ionic. All right, ammonium carbonate is ionic. It has a covalent molecule that happens to be positively charged. It has a covalent molecule that happens to be negatively charged. I guess there should be 2 of them in there. But anyway, for the most part, it's a metal with a nonmetal, but occasionally you get covalent molecules that are attracting each other. It's not a big deal. Don't freak out about it. You get kind of used to what cations and anions can be. As far as a metallic bond goes, metallic bonds are simply the bond that holds a metal together. You're familiar with a metal, all right? Well, what holds metal atoms together, all right? You know metals can conduct, okay? The idea that they can conduct electricity, this is at the heart of it. What you have, if I can just draw some metal ions, like let me have these little green balls be my metal atoms, alrighty? What happens is the metal atoms are there. They have really loosely held valence electrons, so they have these valence electrons around them. And metal ions don't really hold on to electrons very tightly. To be stable, they need to lose electrons. So what happens is that valence electrons are awash, and they can move throughout the whole gig. And they do move throughout the whole gig. And one of the reasons metals conduct so well is if you have an electron that comes into this, that electron can just knock out another electron, knock out an electron, knock out an electron, and out pops a new electron. And so the metal conducts. All right, that sharing, that whole delocalization, that spreading of the valence electrons around all the atoms like peanut butter smeared over bread, that is what holds the metals together. You can recognize metallic bonding because the only thing in your chemical formula is a metal. It's not fancy. You just see a metal, and that's your bonding. Covalent bonding, rather than having ions, rather than just having neutral metals, you have nonmetals and only nonmetals. To become stable, nonmetals need to gain electrons. Well, if a nonmetal is bonding with another nonmetal, they need to gain electrons, and they can't both gain. What they end up doing is they share electrons. So basically what this covalent bond is a shared pair. Okay? So if you have one atom, say the red one, and you have the green atom, they each have a nucleus, and that valence energy level, you're going to have a shared pair of electrons, say those blue little dots. Those blue little dots hang out between the nuclei. If the nuclei have equivalent electronegativity, that's a big long word to spell. If they have equivalent electronegativity, the ability to attract electrons, then that blue little pair of electrons is going to be balanced between the green nucleus and the red nucleus. It's going to hang there in the center. And when it's perfectly balanced, you're going to have perfect sharing. Okay? And if you have perfect sharing, then you get what we call pure covalent bonding. Okay? Nonpolar, there's going to be no pull, no buildup of charge. It's going to be perfectly right down the middle type sharing, which you get only when you have the exact same atom, an H with an H, an F with an F, a C with a C. Don't know why that C's way over there. But to have equal electronegativity, the only time you really have equal electronegativity is if they're the same. Otherwise, it's always going to be slightly different. Some websites, some textbooks will say if the electronegativity is slightly different, it must be polarized. I disagree because, I don't know, experimental evidence says otherwise. Sometimes you can have slightly different electronegativity, like in a CH bond. CH bond, the electronegativity difference is small. It's not that much. Think of a tug of war contest. If you have a tug of war contest, you got one guy pulling, a blue dude and a green guy. They're pulling on a rope and they want to get the little flag to themselves. If they're about equal in strength, that flag's not going anywhere. They might be off just a little bit, but they could be, it's not really going anywhere. And that's what happens in here in these bonds where the atoms aren't identical. If they have close enough electronegativity, then there's not going to really be any unequal sharing. It's going to be minimal. So it's not going to be a big deal. We call that non-polar covalent. All right, I really haven't shown you what a pole is yet, but we're getting there. All right. To get polar covalent, something with a pole, you need a big, strong guy. You need a tug of war over those electron pairs. You got a big, giant guy and a tiny little dude that is going to get butt walloped. Okay, as they tug for it, man, that flag is going to junk right over there. Okay, over to the stronger one. Well, our strong elements, the one that can pull the electron pairs, are them. On the periodic table, if you look in the top right-hand corner of the periodic table, you'll see N, O, F, C, L, and Br. Whoops, screwed that up a little bit. N, O, F, C, L, and Br. They are the guys with the greatest electronegativity. If you got just one of them in there, it's going to be enough unequal sharing to really polarize the bond. One end of the bond, all right, the end with the higher electronegativity, say oxygen, which has more electronegativity than the H. The oxygen is more electronegative than the C. The oxygen is the greater electronegativity, while the electrons move towards the oxygen. And you draw this little arrow, these guys right there, those little arrows, the dipole arrows that show the movement of electrons. So electrons are moving to the O, they're moving to the O. If the electrons are moving to the O, then electron density, negative electrons, negativity, negative things are moving to the electron. And so that electron, that atom, I should say, is going to become slightly negative. It's not a full-blown negative charge because there's still some sharing. Okay. To get back to our example with the overlap of electrons, basically the electrons are moving to one atom over another, but they're not totally owned by that atom just yet. It's kind of like pulling on pizza cheese. It might stretch, but it hasn't broken. So it's just unequal sharing. So where the electrons are going becomes negative. Where they come from, down here from the H or the C, that becomes slightly positive because it's lost electrons. Cool. What you'll learn, buildup of charge. At one end is slightly positive, one end is slightly negative. That's two poles, okay? Two poles. Two poles become what we call a dipole. And a dipole is nothing more than that, just two poles. The slight charge of that bond creates a way that we can create attraction between those molecules. And in our next segment, what we're going to see is how that attraction exists to hold substances together. We're going to have to create attractions that exist within here where we don't have dipoles, but we'll get to that in our next segment. For right now, we're good to go. This is Dr. Mandis. Hope you have a great day.